When I looked at the schedule, I saw that I had the next 3 class periods, so today, Tuesday, and next Thursday, set aside for next section 14.1 on vessel functions. And there is a fair amount of material to cover there. Too much for one day, but I think it could be done in 2 days. And let's see. One of the concepts that is introduced, or at least mentioned for the first time in this class, in that section is the notion of a generating function. And I like generating functions. I talked about them some when I taught a class in discrete math, not discrete math here, but another institution. And there's some interesting things that can be done with generating functions. So I thought before I make use of a generating function in section 14.1 to introduce decimal functions and show a lot of their properties, I would do something different with generating functions today to give you all more an opportunity to appreciate their usefulness. So it was a last minute change, and I was fortunate to find that I already had some notes on this, because I was afraid of doing something on the fly, making a lot of mistakes. But now that I have this, I can maybe settle for only making a few mistakes. I doubt this will take a whole lot of time, so there should be time for more questions if anybody has stuff. Okay, so I imagine that most, maybe all of you are familiar with the Fibonacci numbers. Certainly the most famous sequence numbers out there. So each Fibonacci number is the sum of a previous 2. And you can use whatever numbers as initial conditions, but I guess the standard choice of initial values is f0 is 0, f1 equals 1. So then you would add these 2 to get f2, which is 1. And then 1 and 1 makes 2. 1 and 2 makes 3, 2 makes 5, 8, 13, 21, and so on. So the problem I'm going to use a generating function to solve is this. Suppose we wanted to value a certain Fibonacci number with a large index, like for example, f1000. It would be nice to be able to obtain the value of such a high index Fibonacci number without having to compute all the preceding ones. So do we really need to use this recurrence relation to compute all Fibonacci numbers in between to obtain f1000? Did we, or is there an expression for Fn that is in, I think I've used this term before in this class, closed form. So not involving a summation, just a compact or concise expression, a formula that you can plug into that can be evaluated efficiently to obtain Fn for any index n, taking the same amount of work. The way it is now, yeah, it takes very little work to get f4, but f1000 would take a lot of work. We'd like to level the playing field. And that's where a generating function comes in. So what is a generating function? Generating function for a given sequence is a power series where the coefficients of the power series are the terms of the sequence of interest. So the generating function for Fibonacci numbers is this function of z, where Fibonacci numbers are the power series coefficients, and multiplied by z to the n for each n. And what's interesting is, even though we don't have expressions on hand for Fibonacci numbers, except covers the ones using the recurrence relation, we can actually use this recurrence relation without too much work to get a formula for g of z. And here's how. What I do is I write out what g of z is in dot 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 form. And then I'll also write out g of z and z squared g of z. And what I'll do is I'll write it in such a way that terms with like powers of z are lined up. And the reason why I only go to z squared is because of this being a three-term recurrence relation, each Fibonacci number depending on the previous two. So for instance, if I had a more complicated sequence, like each new value depending on the previous 4, let's say, I'd have to go up to z to the 4 in what I'm doing here. So what I'm going to do is I'm going to subtract the second equation and the third equation from the first one. So on the left side, here we have the right side, but I'm going to move to the left side. That's unfortunate. But I'm going to have g of z times 1 minus z squared. Now, why am I doing that? Because look what I have here. The coefficient of z squared is f2 minus f1 minus f0. But f2 is equal to f1 plus f0. So this is 0. And actually, I'll write out the z cubed term also. That would be f3 minus f2 minus f1 z cubed. Well, that is also 0 because f3 is equal to f2 plus f1. So, okay. Because if I write the recurrence relation as I move everything into one side, z equals 0. Fn minus fn minus 1 minus fn minus 2 equals 0. So that's what I'm using. And that applies for z squared, z cubed, all higher powers of z. That the coefficient of z to the n for all n equal to 2, 3, and on up is going to be this for some n, and therefore it'll be 0. So all the terms of degree 2 or higher will go away. So the way you combine these equations is in such a way as to take advantage of a recurrence relation. So whatever coefficients you have in this equation are coefficients I multiply these by. So here I have 1 minus 1 minus 1. So here I multiply these by 1 minus 1 minus 1, and voila. The only terms that don't go away are these two, of degree less than 2. See what those are, we fill in the initial values. But if 0 is 0, so this term also goes away. And then for a z term, we have f1 minus f0. Well, f1 is 1, and then f0 is 0. So we end up with just z. So all of this reduces to just z. Which allows me to solve for d of z. That is our generating function for Fibonacci numbers. So, if I can find a power series for this function, well, the coefficients of the power series would be the coefficients of this power series. In other words, Fibonacci numbers. The idea is I find the power series coefficients of this independently by whatever means I can, and that will give you a formula for Fn. Now, how you do that depends on what the form of your generating function. So, what I'm going to show you here might not necessarily work for, well, it actually work for a variety of recurrence relations. So what I do is I'm going to perform one of your favorite techniques from calculus 2, partial fraction decomposition on this fraction here. And to do that, I need to factor the denominator. Now, I'm not going to really get to roots now. To reduce clutter in my expressions, I'm just going to say, let's assume that z1 and z2 are roots. The roots are real and distinct in this case, which you would see if you work this out, which I will do later. So for now, you can take my word for it that they're real and distinct. So now I can rewrite this way. So a factorization of 1 minus z minus z squared is z minus z1, z minus z2, and don't forget the minus, because notice we have a minus in front of the z squared here. I think when I first did these notes, I forgot that minus and made everything wrong. And I'm not going to go through the details of partial fractions. I'll simply say that if you were to remember what you did in Cal 2 or looked it up, this is what you get. Fortunately, it's one of the easier cases of partial fractions. You have real distinct roots. Now, at this point, it's not really clear how this helps us, but it's about to become clear. So, in these portions that involve z, so not z1, not the z1, z2, but this variable z, I want to rewrite these fractions, so this one here and this one here, so that I want it to be like 1 minus something. So what I can do is I can divide top and bottom by minus z1 for this fraction, and then divide top and bottom by z2 over here. And what that gives me is, so I have this constant out front. If I have 1 minus 1 over z over z1, then I have 1 minus 1 over z minus z2. So it's very important to have this as a form 1 over 1 minus something. Very important that this is a 1. And you'll see why momentarily. Because I can use a formula for the sum of a geometric series. So this right here is the sum of the geometric series z over z1 to the nth power. And then here, this is a sum, this fraction is the sum of the geometric series z over z2 to the nth power. But what I've done is I've written it in such a way that z to the n and then 1 over z1 to the n are written separately. That way, what we have here is more clearly recognizable as a power series, where this is a coefficient of this one, and then this is a coefficient of this one. Are there any questions up to this point? So every partial fractions and getting one on here was used to take advantage of this formula. Now, we have two summations. They both go for n equals 0 to infinity, so I can combine them in one summation. Both involve z to the n, so I can factor that out. So now I have my power series for my generating function. So just as g of z was defined to be sum of fn z to the n, or I have here gz is the sum of this times z to the n. In other words, fn must be equal to this. And that's what I have here. So this is my first formula, an explicit closed form expression for Fibonacci numbers. We're not done yet, because I haven't told you what Z1 and Z2 are. Also, I can leave these numbers raised to the n, but it's 1 over Z1, 1 over Z2. It'd be nice to write this as some variable raised to the n, or number raised to the n, instead of 1 over that. Cut down reciprocals, those are annoying. So now you can go ahead and get the values of Z1 and Z2. So now remember how I define Z1 and Z2. They are the roots of this polynomial right here. So you could try factoring it. Well, actually, it doesn't factor nicely. But just go ahead and use a quadratic formula on this. And this is what you get. -1 plus or minus square root of 5 over 2. So sure enough, as I mentioned earlier, the roots are real and distinct. So now I define x1 and x2 to be reciprocals of Z1 and Z2. I won't go through the algebra, but what happens when you take reciprocals and you rationalize the denominators? But this is what you get. And notice that it's almost the same thing. The only thing that's changed is that the -1 in the numerator became a +1. It just happened to work out that way. So now this expression that was previously written in terms of Z1 and Z2, and I'm going to write in terms of x1 and x2. So now instead of 1 over Z1 to the n, we'll have x1 to the n, x2 to the n, and then by doing a bit of algebra, but I'm too lazy to show, we have these coefficients. So now, if you're going to work out what is x1 times x2, because notice we have both of those here. So if you work this out, simplify as much as you can, you can find that x1 times x2 is just -1. And you see here, if I took the root of a minus sign and subtracted it from the root of a plus sign, 1/2 would cancel, and you have square root of 5 over 2 in both being added. So x1 minus x2 turns out to be square root of 5. So that works out nicely. And now we have this. And then I fill in the values of x1 and x2. And there you have it. So that is an explicit formula for the nth Fibonacci number. And it seems kind of strange that, and we can see that all Fibonacci numbers are non-negative integers. It seems strange that an expression like this with so many square roots of 5 all through it will always work out to be an integer for whatever power n. So I'll go to MATLAB for a second here. Yes, we're working on paper of Chandler. Okay, so I'm gonna set n equal to, let's say, 4. And I'll set x1 equal to 1 plus square root of 5 over 2. Anyone tell me what this number is, what it's called?
The golden ratio.
Yes, it's golden ratio. And for x2, I could type out 1 minus square root of 5 over 2, but I already know that x1 times x2 is equal to minus 1. So I can do that. So that's the upper root. Okay. So then, fn would be 1 over square root of 5 times x1 to the n minus 1 over square root of 5 times x2 to the n. And sure enough, it is the fourth Fibonacci number 3, because you have 0, 1, 1, 2, 3. I guess it's the fifth Fibonacci number of index 4. This could be the 1000th one. That's a big number. Dang. Well, because they grow exponentially. You get this number greater than 1, you raise to the n power. So that's what happens to these kind of sequences in general. Also, since x2 is less than 1 in magnitude, this part fades away over time. So in the long run, Fibonacci numbers are well approximated by this. So to give an example of not as huge numbers, let's set n equal to, let's say 15. So true Fn, okay, 610. But now, I'm going to remove this term. Pretty damn close. So the larger n gets, the better an approximation the term would be. Done before, so I didn't actually expect it to be that close. But, in general, when you have a recurrence relation like this, some linear combination of these, in this case we have s plus 1 terms of the sequence equal to 0, what you do is you take your coefficients, the alphas, and you form this polynomial. Then it's called a characteristic polynomial of this recurrence relation. You find the roots, and then those roots are raised to the nth power. Now those roots may be complex, they might repeat. In the case, now what you have here are you have powers of n, and these exponents are determined by the multiplicities of the roots. So if the roots are distinct, they're simple roots, only multiplicity 1, you don't have this at all. Whereas suppose you have like a triple root, so it occurs 3 times. You'll have a term involving n and a term involving n squared times the root raised to the nth power. Okay. This theory of recurrence relations is important, for instance, in my research area, like studying because you approximate differential equations by difference equations that are described as recurrence relations. So, and a lot of the theory of recurrence relations relates, the difference equations relates closely to what we learned about differential equations. For example, for each recurrence relation like Fibonacci numbers, the general solution in this form is a linear combination of 2 linearly independent functions, just like for a second order differential equation. If there was a non-zero here, this would be non-homogeneous, then you can express the solution of that recurrence relation as the sum of a homogeneous solution and a particular solution. How would you find that? That relates to methods that you learned about in your first ODE class, like methods of undetermined coefficients, that sort of thing. So there's a lot of commonality between recurrence relations and differential equations and this structure of their solutions. So that's why recurrence relations play a key role in the analysis of numerical methods for solving differential equations. So I end up dealing with these fairly often. Okay. Actually, this is the end of the notes. Were there any questions about how this formula was arrived at? Are there any homework questions? Including from online. What? Yeah. Yes. Oh, okay. Got a response confirming no questions. Please get to go to your concert. Yep. Yeah. Okay. Well, we're considering functions and vessel functions all next week.
Do you expect that to be longer? Maybe
No.
a little bit? Expect to be quicker? Yeah, I timed it well because